Good afternoon. Welcome. I hope this is a peaceful respite from whatever's going on. But welcome. Today we're going to be talking about perceptrons. So perceptrons are like the basic building blocks of neural networks, and that's why it's really important. And we'll be going into how it works and what it is today. So the theory behind the perceptron was created by these two people, McCullough and Pitts, in 1943. So this was like a paper, but it wasn't actually implemented into any machine until 1957 by Rosenblatt. And this machine was called the perceptron. And at that time, it became really famous and super popular. It was all over the news, and he got a lot of funding. So that's why it's known as the perceptron, because he made it really popular. But you'll also see it called the McCullough-Pitts neuron. And this was like the time too, where they weren't coding machines. They were like using wires to move stuff around. So that's like really cool. So the theory behind perceptron comes from neuroscience a little bit. I'm not going to go too deep into it today, but essentially your brain is made out of millions of neurons, right? And this is called an artificial neuron or the perceptron, right? One unit. And we're going to see how they kind of took the model of a neuron and tried to make it mathematical, and how this becomes the foundation of machine learning. So in a neuron, there's two sides almost. And in one side, the neuron gets inputs. And these can be multiple inputs, right? So here, there are what we call dendrites, but you can just think of them as input places. And it's getting multiple inputs. And then somehow it's taking those inputs and creating an output at the very end on the output side, right? So you have 80 billion of these in your brain, and they somehow create your experience and whatever. But essentially, these researchers are trying to capture intelligence. They're trying to understand it. So that's the birth of this type of machine learning. So what exactly does a perceptron do? Okay, I'm talking about the neuron. That does a lot of things, but the perceptron isn't exactly like the neuron, right? And what are we going to do today? So a perceptron just takes in data. So how many of you were at the linear regression meeting? Yeah, I'm seeing a lot of hands. So it's a similar thing where we're going to have data that has features, right? And these features are, for example, if it's just a dog, it could be like the ears, the nose, the eyes, any kind of features of a single point of data. And we're going to put it in the perceptron, and it's going to output a 0 or a 1. So what we're doing is a binary classification. And what does that mean? Let's break that down. Okay. So binary just means 2, right? 0 or 1. So if you know like computer binary, it's zeros and ones, right? So that's why it's called binary. And then classification means we're trying to identify any data we put in as 0 or 1. We're trying to identify it as class 1 or 0. And in any case, for example, if you had points on some graph and you wanted some of them to be red and some of them to be blue, you could be, these are the 0 ones and these are the ones, the 1 ones. Any questions? We're good? Okay, so let's create some notation for this, right? So instead of writing out the entire word of input, right, we're just going to do x1, x2, x3 for input 1, input 2, input 3. And then for output, we're going to do y hat. Because if you remember from linear regression, y hat means your prediction, right? So your neuron or your perceptron, right, is going to predict some class 1 or 0. So there's this idea, right? Let's say you're trying to, like, we're going to abstract this, right? You're trying to go to the movies, and there might be multiple factors to, at this specific time, what you want to decide to go to the movies. For example, maybe the time of day, right? Maybe you're more likely to go to the movies if it's nighttime because that's what you prefer. Or maybe if your friends want to go, right? If all your friends are going, of course you're going to go to the movies with them, right? And then lastly, it could just be like the price of the ticket, right? Maybe if it's more expensive, you don't want to pay the money and then you don't want to go to the movies, right? So those could be various features, right, of a specific movie that you could decide whether or not you want to go, which could be 1, and don't want to go, which could be 0, right? And let's say like not all of those features are going to be as important to you. For example, if your friends really want to go, then maybe the time doesn't matter. You go at 1 a.m. if all your friends want to go to the movies. And the price doesn't matter as much because you still want to go with your friends. You're like, I'll spend $100 if I go with you guys. So the idea is that we want to factor that into our calculation. And we do that with weights. So if you have ever heard of the term, that decision has a lot of weight, that means it's important, right? So important features will have big weights. So for example, your friends you would multiply that by a big number because that makes a big like result, right? Multiplication of product. But if something wasn't important, for example, maybe you don't care what time, you're down to watch a movie any day of the week, any time of day, then maybe we'd want to make that weight really small because any number multiplied by a small number, like for example, 0.1 or 0.001 is going to be really, really small, right? Even if it's exactly 0, then that just means that that feature doesn't even matter, right? So that's what these weights do, right? And I talked about how the neuron takes these inputs and then creates an output, right? How does it like get these all together and make some kind of takes into account all of the inputs? Something we can really simply do is a sum. So that just means adding up all of the weighted inputs. Does that make sense to everyone? Yeah. Yeah, these are like multiply. Yeah. So in a neuron, that happens here at the axon hillock. You just need to know that's where stuff integrates, or they get all the inputs and they're like, let's make a decision of whether or not to send an output. Okay. So the problem is, right, we want classification. And how are we supposed to classify if this is like 0 or 1? Like, what do we do, right? We just have some in like number that is like between 0 and, or that can be any number, like from negative infinity to infinity, because you multiplied and you added. Like maybe this weight is like 2 and this is 3, and then this input is like 10 and this input's like 5 or 0.1 or -1, right? What do we do, right? Does anyone want to guess? No. You want to guess? Yeah. So yeah, this is very similar to linear regression, right? Because you're doing inputs and you're doing weighting. It's all very similar, like, and it's all very similar concepts. And so one thing we could do though is very simply create this situation, or if this weighted sum is above 0, we're going to say this is 1. And if it's below 0, we're going to say it's 0, right? The classification, right? It's just a label, right? And obviously this threshold is arbitrary, but 0 is like a good number because that's between all numbers, right? Does that make sense? So to do that, as I said, we could use this thing called the Heaviside step function. And you're like, okay, this looks super confusing. I can't even tell. No, don't worry. All you need to do is look right here. It's 0 if x, which is the input, is less than 0. And it's 1 if x is greater than or equal to 0. So as I said, you just get that output. And if it's greater than 0, then it's 1. If it's less than 0, then it's 0. Does that make sense to everyone? So let's put that in the diagram. And now we fully understand this diagram right here. This is how we were representing it with this Heaviside step function because it looks like that, right? That's just what we call it. Now, in a neuron, that goes right here. And the idea is that once we reach some threshold, some arbitrary threshold, like that, for example, if that, in that case, it's like if it's greater than 0, right, then it's 1, right? Then we send a signal to the output. So that's all it's saying, right, in the neuron. And that's how we represent it with the math. So now these researchers, they've created a simplified model of the neuron with the math, and they're like, okay, what can we do with this? You know, can we do binary classification, which is what we're going to talk about. So let's break down this algorithm even further. Okay. We like to call this the activation function, but it's just a word, but just think of it as like any function, Heaviside. And then y hat, as we mentioned, is the prediction. So let's just go through this in order so we can like fully cement this in our head. We have the inputs, which are the different features of the data. We have the weights, which tell us which features are more important, which ones could even tell us, oh, like if this is true, then maybe we want to be less likely. That'd be like a negative weight, right? We really don't want to do this if this is true. And then you sum those weights, those weighted features, and then you go to 0 or 1, depending if it's greater than 0 or not. Then you get some label. So one thing we like to do is just add a term after the summation before we do the step function. And we just call that the bias. And it's just adding some number and an additional number for like training to like make the data maybe fit our perceptron better, right? So I wouldn't worry about it. So that's like an excellent question. And that's actually what we might get into in the future, where you use multiple perceptrons together to make them. For example, maybe, I don't want to go too deep into it, but if you had 3 of these, maybe the one that has a greater output would be the classification. Yeah. Okay. Let's just.
I wanted to justify that a little bit further. So we have these weights here in these features, right? These features, let's say the first one is, you know, how many legs something has. The second one is the length of the ears. And the third one is how many whiskers it has. Let's say we're trying to classify dogs or cats. And then we multiply by some kind of weight. Let's say this becomes like 1, or, you know, or maybe this is a really low weight because dogs and cats both have 4 legs. So, you know, it's not going to really care about that. And then length of ears, that's pretty important. So this becomes a pretty high weight. And then weight number 3 was how many whiskers it has. Cats, you know, being a pretty good classifier, this becomes a pretty strong weight. But let's say they all happen to be positive, and then we sum them up. And if we didn't have bias, we'd toss them through the step function. And all of these summing them up, because the weights happen to be positive, it would always choose one all of the time because the step function would always send it positive, and it might try and shrink all the weights together, but that would, take a lot of time. So we have this bias feature right here that we could just set to like, and it would learn to make it a negative number. And these could all be positive, and it wouldn't have to worry about the fact that the step function chooses between less than 0 or greater than 0 because we have this bias here to shift it.
Does that make sense to everyone? It's good. That's what you need to know. Okay, so am I going backwards? Okay. So we just went through the entire perceptron, okay? So you know everything about the perceptron now. You know that you take in the features, multiply the weights, you sum them, you do activation, which is the heavy side, 0 or 1, and then you get an output, 0 or 1. So let's do that together with an example, right? 0.5. So there are input features. This is x1, x2, and our weight feature is 1, -1, right? And what we're going to do is we multiply and sum. So 0.5 plus 1 is what? 0.5. Yeah, times. Did I say plus? Okay, multiplied. Yeah. Multiply. And 0.8 times -1 is -0.8. So then 0.5, 0.5 minus 0.8 is -0.3. And our bias is 0, so it's just -0.3. And then -0.3 is below 0. So then the classification is 0. So I have 5 more problems here. Why don't you guys get into groups and try to figure them out? I'll give you guys 5 minutes. Should be pretty. I want to give you guys some like practice exercising with this. And the equations are here too. So if you need help, right here and here. You're covering the. You put it on the top corner right here. Okay. Yeah, I mean, this is empty.
Raise your hand if you're still working. I need more time.
Okay. Oh, what? What happens?
Uh,
Okay, who thinks they have the answer to the first one? Yeah. Zero. Did everyone else answer zero? Yeah. Did you ever? Okay, you were raising your hand that you answered zero. Okay. Um.
walk us through how you got that. Perfect.
Nice. Okay. How about the next one? Does anyone else want to try to give that a shot? How about you? One. Do you want to explain real quick? Great. Great. How about let's just do the last three in one shot because it's pretty similar. Does anyone want to? You in the back. 110. Is that what everyone else got? Do you want to quickly explain 110? Yeah, the same. Okay. 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 Great. You did it. Clap. Let's clap, everyone. We did it. Okay. So I have a bonus question for anyone that's taking CSE 12, which is just for fun. But can anyone tell me what the gate is? Like if this is an a gate, like a XOR gate, but this is not XOR. What would it be for the last four? You want not or? Does that what everyone else thinks? I'm hearing NAND over here. You think NAND? Do you think NOR? So I have NAND. That's the answer I have here. So yeah, I think it's because if you the and is the 1 1, right? That would be and then it'd be the opposite, right? These three would be zero, and then this one would be one. If it's an and gate, then NAND is the opposite. So NAND gate, very cool. It just shows you can do like gates with perceptrons, but that's just for fun. Okay, so we're gonna show you guys how to do this, the code real quick. So feel free to pull up your laptops, type in this bit.ly. But after you do that, you're gonna hit open in Colab, and if you want to save it, you can save a copy in Drive. Yeah. I would type this in if you have your laptop, because then you get it on your laptop and it's better. But if you only have your phone, then that's what the QR code's for. Or your iPad. That also works.
Raise your hand if you're still getting it set up.
Okay.
All right. So I'll make it more like official.
Realizing this code is using documents. Right? This code's using doc products. Let's do it. No, but I think that's on the next slide here. Or no, it's no. Yeah.
There we go. It's perfect.
Oh, it is. Is everyone on the Google Colab now? Okay, so one thing we're gonna do real quick is so we just for the code, we're gonna need to know what a dot product is. And that's because when we're doing that summation, that can be represented as a dot product where these are like A1, A2, A3, B1, B2, B3 of vectors, right? And if you do the dot product, it's the same as doing the summed multiplication, right? So if this is the input and this is the weight, it's just a dot product. Does that make sense to everyone? Okay. So let's get to the code. Here we have a class of perceptron, and we have the weight vector and the bias vector. In order to predict, we have to do the dot product, right? Do we have the stand? Oh, it's broken. Okay.
Yeah, it won't show up.
Um, so what we need to do is create a dot product. Right? And in Python, it's really easy with PyTorch, the library. All you need to do is torch dot dot. Okay. And then we will take the weight vector and take the dot product of the weight vector and x the input, right? So we define the weight when you create the perceptron. And then whenever you predict, right, you're putting in some features, some data. And then, as you mentioned before, you want to add that bias to make the calculations easier for the perceptron or the neuron. Right. And we're going to just call this like the activation level, but it doesn't, it's a variable.
And if you have any questions, raise your hand and I can come back.
So what do we do with the output of the sum dot vector? Does anyone want to raise their hand? Remember, we do the weight multiplication, and then we sum those weights, we add the bias, that gives us some number, right? The activation. How do we get our classification? Exactly. So yeah. So we're going to do that by y-hat's prediction. 1, if the activation of the item is greater than or equal to 0, right? Else 0. So it's 1 if it's greater than or equal to 0, otherwise it's 0. And we've done it. We just got to return y-hat instead of none, our prediction. And we've totally, fully coded Perceptron. So what you want to do is make sure you run all the cells in order. We're going to run it. And you can see here, that table we just did, we're going to test it with the code to make sure our Perceptron's working correctly. And here, you have to wait for the code to run.
Also, if anyone's getting some weird errors, make sure there's that runtime button at the top. If you click runtime, then run all. It'll run all of your cells in order, and oftentimes errors can come up if you forgot to run a cell or missed one or something like that.
Yeah, I would restart session and run all, because then
yeah.
So then, right, okay, let's look at this table. What do we get for an input of 0.5 and 0.8 with the weight at 1.0 and negative 1.0? We got 0. And the next one we got 0. And then we get the NAND gate, right? 1110. So our Perceptron's working 100%. It's working well, right? It's working good. Any questions? Great. Okay. There's slideshow mode. So here we're going to try and give you a geometric intuition of the perceptron. So to simplify this, to make it easier for everyone to understand, let's just say the bias is 0. Get rid of bias, okay? And then we're going to only have inputs of 2 features so that we can plot it on a 2D grid. We know by this equation, if you haven't seen this equation before, don't worry. Just trust me, that's true. That the dot product of 2 vectors is equal to the magnitude or the length, just a positive number length of those vectors times the cosine of the angle between those vectors. So I already mentioned this, but to convert, we just do dot product, right? And the intuition here is shout outs to high school geometry. If your cosine theta is greater than is an acute, if you have an acute angle, sorry, let's just refresh that. If you have an acute angle, that means theta is less than 90 degrees or pi over 2 radians, then the cosine theta is going to be greater than 0. It's going to be positive. If the angle is exactly 90 degrees, then your cosine theta is going to be 0. And if it's an obtuse angle greater than 90, your cosine theta is going to be less than 0, right? So what that means is here, if the vectors point in the same direction, your dot product should be positive. If they point in opposite directions, they should be negative, right? And that's why you can kind of say if they're positive, if the dot product is positive, they're aligned. And if they're not, they're disaligned or in opposition. Okay. So as I mentioned before, what we're going to do is transform, instead of A and B, we're going to think of in terms of W and X, right? The weight vector and the input vector. So here, let's just reiterate. Someone answer me. If W and X are acute, is the dot product going to be positive or negative? Negative? Does anyone else have a different answer? How about let's go back to here. So if the angle is acute, which means they point in similar directions, the angle is less than 90, the value is going to be greater than 0, right? Actually. Yeah. Does everyone get that? Yeah. So theta here, this angle. Yeah. Hmm? Yeah. So here, they're acute. So the angle here, right? Does that make sense to everyone? Is everyone comprehending this? So positive, because these two values will always be plus, right? Because it's just talking about length, and length is always positive. There's no such thing as negative length. Yeah. So given that we know this, what would the classification of these 3 points be? I want to give you guys 3 minutes to think about this. Can we make a timer for 3 minutes? And after that, we're going to try and figure this out together. You put on the left. Topmost, yeah. And remember, we're setting bias to 0. So bias is just 0. And then I didn't draw 90 degrees here, but pretend this is 90 degrees. So this is a right angle, right?
Does anyone need more time? Say raise your hand if you need more time.
So everyone got answers? Okay. All right. So how about 1? Does anyone got answer to 1? Yeah. 1? What's your reasoning? That makes sense. Do you have any? Does anyone want to try 2 and 3? Or does everyone also think that too? Yeah. Do you also want to try 2 and 3? Yeah. Go ahead. Yeah. Uh-huh. And then 3? Is that what everyone else thinks? Anyone else want to make a comment on that? Yeah, so that's what I have too. So this is where we come to this idea of a decision boundary, or like the edge of classification, which means if you have this weight vector, any point here is going to be classified as 1 in this entire region of space, right? And if you have this weight vector, then anything here is going to be classified as 0. Does that make sense? Is that cool? So you'll see something like this in like K nearest neighbors, where like all these points in one area are going to be classified as one way, and another points in another way area are classified as in another way. And that's where you get this concept of decision boundary. And this is just a decision boundary of a perceptron, right? And then you can imagine if this is 3 features, then it might be a plane, right? But that would be too complicated. So then how do we learn these weights, right? One way to do this is gradient descent. And if you remember the linear regression lecture, very simply, we're not going to go too much into detail today. You take the derivative of the weights with respect to loss, and all that tells you is which way is the greatest increase of the weight to make a greater loss. But what we want to do is go in the opposite direction, right? So one way you can think of it is like a ball rolling down a hill. If you get the slope right at any point on this, that's going to be going in the positive direction. That's going to be going up the hill. So you want to go in the opposite direction. So you subtract, right? You subtract the derivative. So let's go back to the notebook. What we're going to do is code. What we're going to do is code this up again. Just for like reiteration's sake, does anyone want to tell me what to code here? Exactly the same as the first one. Let me give you a hint. It's that weighted sum. Starts with the, you want to guess? Course dot between the weight vector and the input vector. So there's no bias, right? So we just get rid of the bias. We don't need bias, right? And then does anyone want to tell me what you do after that? Let's go back to the earlier slide. So we did the weighted sum with the dot product. Then what do we do here? What is this? Yeah, the if statement, right? Does that make sense to everyone? Is that clear with everyone? Yeah, okay. Seeing nods. No, we're not doing bias. So then 1, if the activation is greater than 0, else 0. What is happening here? Some spacing thing.
The last time was insight.
The with.
There we go.
Okay, there we go.
There you go.
Okay.
Remember, if you have any questions, feel free to raise your hand.
So remember, this is how we code the perceptron. Run this. Let's put some data together. So I'm not gonna have you code anything else, but here you do. Yeah, I'm gonna restart and run all because I forgot to run some stuff. Question? Huh? Yeah.
Meeting recorded, yes. On the Discord, there should be a recordings channel, and as soon as we finish, we'll save the recording and upload it there.
Okay, so As we can see, over time, the perceptron is going to change the weight such that this decision boundary will split these points. And then you get your classification, right? So then these are 1 and these are 0. Does anyone have problems with their notebook? Cool. Great. What time is it? 4:50. Do we end at 5 or 5? Okay. Great. So for something to end off with, we're just gonna watch a small video. It's just a historical video about what they thought the potential of the perceptron was. And well, what you can tell is that we just did binary classification, so it can't actually do all this stuff. But you can see why it's became really famous back in the day, because they're going to claim a bunch of stuff that isn't true until like now.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned.
How much it
While promising, this approach to machine intelligence virtually died out.
Yeah.
In the 1950s and 60s,
it gets resurrected in the form of multi-layered perceptrons, but we'll see that later. Great. Thanks for coming, everyone. Next week, we will be covering decision trees. So get excited. Do you have anything you want to say?
Yeah, so next week's decision trees, and then we have practical uses of AI, and then we have our break for Thanksgiving, and then we have our Sky's No Limit. So everyone who's doing those, we're going to have a big kind of presentation and celebration for those here instead of a normal presentation on week 10. And yeah, thank you guys for coming. Also, before you guys wrap up and go, who here has heard of a neural network? Who here is excited to learn about those? I know I was when I first attended some of these meetings. This perceptron, the stuff we went through with the weights being multiplied by the inputs with the bias and the activation or the heaviside step function, that is the building block to neural networks. Neural networks can be thought of as essentially a bunch of those stacked on top of each other, and then those are all combined in a series. So this is kind of your introduction to neural networks. Quarter 2, so winter quarter, we will be focusing almost exclusively on neural networks. So right now we do a lot of like AI algorithms and stuff like that. But the more, I think, exciting stuff happens quarter 2, winter quarter, when we're going to be covering neural networks. And this is probably the most important presentation to see to get ready for those. So yeah, just if you understood kind of the how an input gets passed in, multiplied by weights, added to a bias, and then the step function works, then you're well on your way to understanding how neural networks work. Thank you guys for coming. Here's the Discord if you don't have it, the link tree, and then as always, a feedback form. If you guys could fill it out, that would be amazing. Thank you guys for coming. We'll be here for a little bit longer, and yeah. Thank you.
We should probably add